Hello everyone, in this video we're going to solve two problems related to static equilibrium. So I highly recommend you to watch our previous videos on torque and static equilibrium and also the Newton's laws. So here we are with our problem number 1. For this problem, we have this frame here with several loads acting on it, okay? And we want to replace the loading on the frame by a single resultant force and also specify where its line of action intersects member AB, right on top here, measured from A, okay? So we have three loads on top of this frame, okay? So we have three forces pointing down, one pointing to the left here, and we have a torque that's been applied at point A. It seems complicated, alright, but we're going to see that's actually pretty simple if we apply the static conditions, okay, the conditions for static equilibrium. We can start by the forces in the x direction must be 0, okay, for static equilibrium. Well, in this case here we just have one force that's pointing to the left, okay? So our single resultant force, the x component of our single resultant force must be 200 pounds pointing to the left, okay? We can do the same for the y component. So we have three forces pointing down, this 300 pounds plus 200 plus 400 pounds. So our y component of the single resultant force pointing down must be 900 pounds. Okay, so we have the x and y component. We can calculate our single resultant force vector, okay, Fa, which is 922 pounds. All right, very good. We want now to find the angle we apply this force, this resultant force, in order to be equivalent to all these other forces here, okay? So we can calculate it using the tangent of the angle. Okay, we have a triangle here that's 200 pounds on this side here, okay, and 900 pounds on the opposite side. So our angle is 77.5 degrees. Very good. Now we have the magnitude of the resultant force, of the single resultant force, and the angle we must apply this force here. But we want now to know where it must be applied, okay, the line of action. Okay, measured from A, right? So now we can apply the torque, okay? So for the equilibrium, all the torque acting on this beam, the sum of all the torques clockwise and anti-clockwise must be 0. We have a torque from our resultant force, right? Just one thing, we're dealing with this beam here, AB, okay? So the only force that makes this beam or the entire frame turns into this direction here, anti-clockwise, is our y component, okay? So it's the 900 pounds downwards. So this force here, this component pointing down, 900 times a certain distance from A, R, okay, is the torque applied, the torque resultant from all these other forces here, okay? So it's the 200 times 3 feet plus the 400 times 7 feet, okay, plus the 200 right here times 2 feet, that's the lever arm we have here, okay, plus, minus this torque that's being applied on A, 600, okay. Note that this force here, this load, does not interfere because it's being applied exactly on point A, okay, so it has no interference. So now we have our equation. We can just find R, and R equals 3,200 divided by 900. That's 3.56 feet away from A. So our single resultant force has a magnitude of 922 pounds that's applied 3.56 feet away from A in 77.5 degrees right here, okay? And that's the answers for our problem number 1. So here we are with our problem number 2. Okay, for this problem we have a beam, this inclined beam, we have a pin at A and a roller at B. Okay, have this force here acting on the roller and this torque that's been applied on the end of the beam. Okay, and we want to calculate the reactions at the pin and the roller. Before we start, remember that when you're dealing with a pin, we have reactions on both directions, X and Y, okay? Now for a roller, we have reactions only in one of the directions. In this case, the roller can move to the right and to the left. It can move into the X direction, but does not move into the Y direction. So the only reactions we have on B are in the Y direction, okay? Now let's start by calculating the angle we have here. Okay, it's an inclined beam. So we have this triangle here, this right triangle is 12 by 5. We can calculate this angle by the tangent of the angle. Okay, this angle is the same here. So the tangent of this angle is 5 divided by 12. Okay, so the angle itself is 22.62 degrees. Very good. Now let's apply the conditions for static equilibrium. Let's start at point B, okay, to find this reaction in the Y direction. Very good. So we have our condition here. The sum of all the torques must be 0. So FBY times 8, that's the distance here, is equals 800, the torque right here, plus 500 times the distance here. Okay, that's the distance of the beam here. Okay, because we're dealing with the Y component, so we have 8 divided by cosine of 22.62. Okay, these forces, okay, are making a torque that makes the beam move into the clockwise direction, right? So our reaction needs to be in the anti-clockwise direction. So probably this force FB here is pointing up, right? We have components pointing down and a torque into the clockwise direction. So the reaction must be on the opposite way. So this force must be up, okay? And we have now doing all the calculations that our FBY is 642 newtons. Very good. We have the reaction at the roller B. Now let's go to the pin A and let's apply the force conditions. Okay, so the sum of all the forces into the X direction must be 0. So FAX must be equal to the X component of this force here. Okay, so that is 500 times the sine of the angle. And this probably is pointing to the left because the only force that's acting is this one, and the X component is actually pointing to the right. Okay, so this FAX is 192 newtons. Now we can do the same, but now for the Y direction. Now let me show you something here. Okay, so for this force to be in equilibrium, okay, let's consider that's actually pointing down. So we have that Fay minus this force here pointing up plus the component of this force, the y component of this force that's pointing down. Okay, this must be 0. So we have an Fay of 180 newtons pointing down. So see that you have to assume the direction of the force, okay, to do the calculations. If I assumed it to be pointing up, this resultant here would be actually negative. So the magnitude would be the same, but this negative sign would tell me that I assumed the wrong direction, okay? So for your calculations, always you have to assume the direction of the force, okay? If you get a negative result, it means only that the direction you assumed is wrong. So it's the opposite direction, okay? I could assume that this force is pointing up, so this result would be negative. So the only thing I needed to do is to invert the vector here, okay? So that's it. That's the result. These are the results for this problem. Hope you enjoyed and see you next time.
Now that you watched this video, you're one step closer to achieving your academic goals. Well done! There's always more to learn, so check out our other videos and don't forget to subscribe.